Hello, my name is Thomas Carnahan, and this is the third paper for my Assignment 3 for Compex 52921B, Engineering Self-Adaptive Systems. The title of this paper is Smart Cities of the Future as Cyber-Physical Systems, Challenges and Enabling Technologies. The authors of this paper are Antonio Puliafito, Giuseppe Tricomi, Anastasios Zafeiropoulos, and Symeon Papavassiliou. This paper was published in Sensors, Volume 21, in 2021. Interconnected smart cities allow for the easy collection and distribution of information between systems within the city. This allows for improved efficiency of services, transportation management, decision-making, public health, and other systems. The main issues that need to be dealt with when implementing smart cities include the energy efficiency requirements of the system, as a large amount of sensors will be required, the architecture of the system, including the hardware implementation, the protocol stack design and how these sensors communicate with a remote server, the protocol stack design, the implementation of these sensors, and security to ensure privacy for users of the systems. One component of smart cities is software-defined buildings. These buildings consist of multiple layers, with each layer controlling the one below it. The top layer is the control layer. This contains human interfaces in which a user will interface with the system. The middle layer is the coordination and management. This aggregates data and makes decisions based on this data. The third bottom layer is the infrastructure. This consists of the sensors, which is collecting data from the environment and controlling the environment. The entire city will consist of 4 layers, the top being the stakeholders. These are the users of the system. The second layer is the application layer. This is services that users may be able to interface with. The third is the management layer. This layer is constantly monitoring, profiling, ensuring quality of service and security of the system. The bottom layer is the infrastructure. This is where data is collected, managed, stored, and where changes are made. Complex cyber-physical systems consist of a collection of smaller cyber-physical systems. These may be owned by private or public owners. Service-level agreements may be made between owners to share data or resources. These may utilize cloud computing, in which data is processed in a remote server, fog computing, in which local devices are connected to a remote server, or edge computing, where data is processed entirely on devices. The Internet of Things will play a large role in smart cities. This includes the connection of physical and virtual objects that a user may interact with virtually, but will have real-world changes. The challenges of the Internet of Things is the interoperability between devices, the development and management of applications for these devices, the need for improvements in intelligence and automation to process data from these devices, the design for humans, designing applications which humans can easily interact with, and the large amount of data storage, management, and representation that will be required. Processing data from IoT devices may be done on the devices themselves, though the challenges of this is the resource constraints and the fluctuations in workload that may occur. To combat this, we may distribute the computations between the cloud and the edge devices. This may take advantage of new technologies such as 5G. We may also use application orchestrators such as Kubernetes to manage resources and applications. This requires IoT applications to be broken down into components or microservices. These may be manageable, scalable, and more reliable. These may also use generic functions so they can be reused or used in another application. IoT application management must also be considered, with the distribution of computations between the cloud and the edge, relying on the resources, efficiency, and performance required. The system status must also be monitored to ensure that it is healthy and that no failures have occurred. The synchronization of updates to devices and new workloads must also be done. Infrastructure management consists of network and device management. For network management, IoT slices may contain clusters of IoT devices. These may utilize massive machine-type communications, such as 5G, to communicate between large amounts of devices, or ultra-reliable low-latency communication when low latency and performance is required. Device management may be done using digital twins, in which a digital representation of the device is managed by the orchestration system, or IoT agents within the device are presented to a user to control individual devices. The Stack for Things cyber-physical system framework handles the authentication, remote access and management, and remote customization of the system. The Stack for Things framework consists of a data center that contains the S4T Iotronic module. The user may interface with this using either a web browser or a command line client. Geo-distributed IoT devices then contain the S4T Lightning Rod module, which communicates with the Iotronic module in the cloud. The Stack for Things virtual networking framework utilizes Neutron. This creates replicated local area networks using virtual networks. This allows for communication between IoT devices and the cloud. Each IoT device is assigned an individual port. Processing is largely done in the cloud. This allows for lightweight processing on nodes and also allows the system to be scalable and reliable. The Stack for Things Edge function as a service utilizes kindling to allocate functions to devices. It also uses Xun to create the required containers on these devices. Iotronic is used to route requests from users to device IPs and ports. A WS tunnel is then used to send these requests to the requested device. Stack for Things secure web service uses Designate to expose devices to the internet. It also uses it to assign URLs to devices so users can interact with them. The ACME protocol is used for issuing certificates and to validate the user. One use case of cyber-physical systems is the smart city skeleton. This consists of 3 layers: the infrastructure, management, and presentation layer. The infrastructure layer consists of IoT devices. The management layer controls and manages data from these devices and sends commands to them. The application layer contains applications that a user may interact with to control these devices. Both the management and application layer may exist within the cloud. The second use case is the exploitation of the computing continuum. In this use case, functions are deployed to devices. Devices may then communicate with each other to find faults in a system and make decisions based on data. This may be then used to notify the user of any changes in the system. An example of this is machinery. If one machine was to exceed max temperature, it would turn off power to the machine and notify the machine operator. The third use case is the cooperation between multiple cyber-physical systems. An example of this is traffic management, in which smart traffic lights may communicate with vehicles to optimize vehicle speed to reduce the number of red lights that the vehicle encounters. This may also reduce vehicle emissions. Computational load may also be spread between the vehicle and the traffic monitoring systems. In conclusion, cyber-physical systems offer many benefits to cities, including efficiency for services, transportation management, decision-making, and public health. Challenges that may need to be looked at include interoperability between applications and devices, the development of applications for these services, how this system will be implemented, and access and security. My critiques of this implementation include who pays. Who pays for the cyber-physical systems when they're shared between multiple users? There's also privacy concerns in ensuring that data does not become public. There's also reliability, as we don't want traffic systems failing within a city. Lastly, there's energy consumption, with large amounts of devices communicating wirelessly using 5G technologies. A large amount of energy will be consumed. Thank you.